Hello and welcome. In today's video, we are going to introduce some of the most important basic data structures. When working with large amounts of data, the way data is organized can make a huge difference in performance. Proper data organization is what turns a basic program into an efficient and scalable system. So what are these structures and when should we use each one? Let's start with vectors. A vector is a dynamic array, which means it stores elements in contiguous memory. We can access each index with the time complexity of O of 1, meaning a vector can access its indices really fast. A vector can also grow and shrink in size. The vector keeps track of its size, which is the number of elements currently stored, and its capacity, which is the reserved space in memory. We can add an element to the end of our array using pushback, and this takes O of 1 time. When we use popback, the last element is removed. This operation takes O of 1 time, making it very efficient. However, if you want to insert an element in the middle, it would require the data to be shifted, which will take O of n time. Vectors are great when you need fast access by index and dynamic resizing. Here's a C++ demonstration of vector standard template library. So we will first include the library here. Then we define the vector like this. We can push back, access any element, pop back, and we can get the size and capacity of the vector with this syntax. Moving on to the next, we have the stack. A stack follows the LIFO principle, which stands for last in, first out. You can think of it like a stack of plates, and you can only add or remove items from the top. The push operation adds an element to the top. The pop operation removes the top element, updates the top pointer, and both run in O of 1 time. Stacks are commonly used in function calls, undo operation, and expression evaluation. In C++, we will include the stack library first. Then we can define our stack like this. We can perform the push operation like this, and we can access the top element with this syntax. And simply with .pop, we remove the top element. Now let's look at the queue. A queue follows FIFO, which stands for first in, first out. You can think of it as an actual queue of people where the first person in the queue is served first and new people will join in the back of the line. So elements are added to the back and removed from the front, and both operations will take O of 1. When the element in the back reaches the end, the back cycles around into the 0th index. You can think of it as an array that is shaped like a ring, which is exactly what a circular buffer is. This makes queues ideal for situations like task scheduling, BFS in graphs, or anything that only requires access to the front and back. In C++, we define our queue like this. We use push to add to the back of our queue and pop to remove the element in the front. And we are able to access the front and the back of our array using these syntax. Moving on to the next, a deque or a double-ended queue is more flexible. It allows insertion and deletion from both the front and the back. Because of this flexibility, deques are useful in problems that need both stack-like and queue-like behavior. In C++, we first define the deque. We can push from either side simply by specifying which side we want to add our element to. We can also access the front and the end similar to queues as well as the size of our deque. Finally, a linked list stores elements in nodes. and each node contains the data and a pointer to the next node. Unlike vectors or arrays, linked lists do not store elements contiguously. This means insertion and deletion are very efficient with the time complexity of O of 1. This is because no shifting of element is required. Additionally, access costs differ depending on whether we use the index or the pointer to that node. Now let's say we want to insert 15 after 10. First, our new next should be pointing at the same thing our current next is pointing to. Then we will need our current next pointer to point to our new node's data, which is in this case 15. So now we have 15 inserted in between our linked list. Now, if we want to delete 20, we want the pointer that is pointing to 20 to skip it and point to the element after 20. And after this, we simply delete 20. So the time complexity of insert and delete is O of 1, but random access would require O of n. In this C++ implementation, we used singly linked list, which is one of the few types of linked list. We will start by a structure that will contain the data and a pointer. Then we will follow by making the class linked list. We will make an insert front function. This does new node allocation, points it to the old head, and updates the head to the new node. Next, we will make another insert function which does the insertion after a given node. It will first check if the previous pointer is not empty, then allocates new memory, and as we explained in our example, links the previous node to the new node, and link the new one to the current. We will also make a delete function that deletes a node given a previous node. So first, we check if either previous data or its pointer is empty. If it is not, we will define another node so that we could use it for deletion. Then, we will make the previous pointer to skip the node and finally delete the defined node. Here is a quick comparison of efficiency for every data structure we discussed. If you enjoyed this visual explanation, follow us for more algorithm content. Subscribe to the AUS Algorithm Club on YouTube and follow us on Instagram for updates and short explanations. Thank you for watching.